Okay, good morning, everybody, and welcome to one by the last lecture in this course on the automated labs and automated experiment. So today we are going to talk about the multi-fidelity and multi-objective Bayesian optimization. So the first obvious thing is, why do we need it? And the answer is that we need multi-objective Bayesian optimization for scenarios when we want to optimize more than one parameter simultaneously. We need the multi-fidelity and multitask Gaussian processes as the way to use the information from more than one source, or have the Bayesian optimization workflow fulfill more than one task at the same time. So there is quite a lot of confusion about these methods, because the vast body of the literature that exists about these models, first of all, tends to be difficult to understand, at least if you are the domain scientist such as myself. And secondly, in many cases, it gives the mathematical principles, but not necessarily the actionable codes. So now the codes are becoming available, so it becomes possible to actually use these tasks these methods in the real experimental life. The catch here will be that multi-fidelity and multitask can refer both to the way how the Gaussian process is constructed and to the type of problems that we can use it for to solve, which basically means that we can solve the multi-fidelity problem to Gaussian process to solve multitask problems, and multitask Gaussian process to solve the multi-fidelity problem. So there can be a considerable confusion here, and we are going to look at the example of what the problems can be and what the solutions can be. And then on Monday, we are going to talk about how we can use Gaussian processes to organize the workflows with the multidimensional data, and how we can start to approach the problems of orchestration of multiple research tools and theory and experiment. So these are well-established areas. We are just going to illustrate how they work. These are a very new area of research, which basically develops on the maybe not daily, but at least weekly or monthly basis updates. So here you will kind of have a look at what is the current level of thinking in these areas. So let's make a short referral back to the original slide that I've shown you at the opening of this course. And here the idea is that generally we need optimization in order to make our labs run better. But if we look even at the simple lab, like lab with, let's say, 10 people working on the synthesis of the hybrid perovskite materials, the workflows in any experimental lab would be fairly complicated. For example, we can start with the reagents. We can use them to make the combinatorial libraries of microcrystals. Once these libraries are made, we can close the loop by studying their optical properties. And of course, we can envision the Bayesian optimization loop, where we explore the compositional space of the reagents by making the microcrystals and studying optical properties such as bandgap or stability. This would be an example of well-defined Bayesian optimization workflow, and we can solve it through the pure data-driven methods like a classical GP, or we can use the physics-based methods such as structured GP in cases when we know something about the physics. For example, we can hypothesize what is the composition dependence of the bandgap. So that one is relatively easy. We can also hypothesize what is the composition dependence of, let's say, stability. That one is considerably more complicated. So this would be an example of the single Bayesian optimization workflow. However, in many cases, we use exactly the same reagents to select the candidates for the thin films. And once we make thin films, we can use them to make a device, or we can use these films and work with our colleagues that take the imaging data to visualize the microstructures. So notice that if we use the films to make a device and then we measure the device property, We also have a standard Bayesian optimization workflow. When we choose the reagents, we make the films, we measure the property of the device made with the film, we use the device property as the reward function to help us select the next ratio of the components. So this is an example of the absolutely standard by now Bayesian optimization loop. And there are a lot of startup companies like Ionix which are working in this area and trying to use the Bayesian optimization, for example, to make a better electrolytes to the batteries. But sometimes we do sometimes we actually want to solve the couple problem. For example, we know that combinatorial synthesis is relatively fast, and the characterization of the combinatorial library is also fast. Making films takes considerably more time, and measuring the device property takes even longer time. So the problem that we have in the real lab is how can we use the combinatorial libraries and the property measured on the combinatorial library in order to help us make better films. Notice that the difficulty here is on two levels. First of all, we implicitly assume that whatever we know about the microcrystal of certain composition would be correlated with the properties with the film of the same composition. Sometimes it is the case. We generally expect that the band gap would be the same. It depends only on composition, but not everything would be the same. So for example, stabilities can be correlated, but not necessarily the same. Second problem is that ultimately we are interested in the device functionalities. So for example, the current, the efficiency, what's not. So this is the property that it can be measured only on the level of the device made out of the film. So we are never certain what is the relationship between the optical properties and stabilities and the device functionality. This is something that we have to discover. So today, we're actually going to talk about how this type of things can be done and what type of Bayesian optimization is necessary for that. Notice that the second part of the challenge, how do we work with the high-dimensional data set and how we navigate, how can we use more than one instrument at the same time, that's something that we are going to talk about on Monday. So I've shown you the example of how the general Bayesian optimization workflows work like, and they can be defined over the low-dimensional parameter space, such as the parameter space like as a composition. They can be defined over the high-dimensional parameter space, such as molecules, structural patches in microscopy, or molecular structures. So in all those cases, if our parameter space is simple or complex, if we measure a complex or simple descriptor, we basically have the same workflow where we define what the physics we're interested in. So this is our scalarizer. For simple measurement, we measure the parameter of interest directly. For complex measurements, we can introduce a scalarizer. So we'll talk about it as well. The role of the scalarizer in all cases would be the reward or objective function. That's what we want to improve. And then the workflow is always the same. So we train the model. For complex data, it would be the deep kernel learning model. For simple data, it would be the Gaussian process or the structured Gaussian process. And then we choose the next place to do the measurements or next location to the phase diagram to synthesize the material. And the definition of this myopic workflow allows us for multiple points where we want to intervene as humans. So we can define the initial targets. In many cases, people say that we initiate our Bayesian optimization workflow randomly. That's a way. That's definitely not the best way. There are much more efficient strategies to do that. We need to define our objective function. So remember that objective function is the key element of the Bayesian optimization workflows. And what's very, very important is that if we plan to use the Bayesian optimization in the real world problem, that actually becomes the biggest part of the job. And I will show you the example where it actually is necessary. The reason why it is a big part of the job is because the reward function has to be available at each step of the experiment. So if we're making the microcrystals, we cannot use the properties of the film as the reward function. It needs to be something that we can measure on the microcrystals. And practically, the way things are developing now is that design of the reward functions will become the biggest challenges for us as an experimentalist, because unlike our colleagues in the theory field, where the reward functions are relatively well defined, building them in experiment is actually difficult. However, once the reward function is created, then everything else is basically using the existing optimization frameworks. And by now, these are well developed and universally available. So we are good to go. And the important thing that we also can easily add the cost component. So our policies balance exploration and exploitation, but it is trivial to add the cost for those as well. And the way that we add the cost is simply we divide our acquisition function by the anticipated cost, and then it becomes kind of easier. So the problem with the simple optimization workflow is that it is useful for individual tasks in the research labs. It's absolutely not enough for actually doing research when you have multiple tools, multiple people, and multiple problems. So why it is the case? So first of all, because as I've showed you on the example of the hybrid perovskite workflow, we always have to make decisions. And each decision that we make opens the additional decision space. And obviously, we are almost never going be able to go back and make a different decision. So it is called counterfactual situation. So we always think that, hey, maybe I should have done something different. That's sometimes makes sense. Maybe this decision was wrong. But the problem is that if you go back and think about the counterfactual decision, what if, then you never know what would be the next step. So what would have happened otherwise? Maybe all of those alternatives would be worse than the one that you originally taken. So basically, the most part of the decision space remains unknown, because realistically, we can just go from one decision to another. We can try to make them as best as we can, but we cannot go back and sort of reload the game. So that means that if we run our automated workflows, we actually need to have some ways to actually make decisions and choose what is the next measurement we are going to take. So I made the material, I characterize it. Can I select, should I do the X-ray next or micro-Raman next? Second thing that we care is that whenever we deal with a real world problem, we typically care more than about one reward function. So for example, if we test the battery is not determined by one parameter, such as cost or power density. So to make a good battery, we need to balance stability, cost, manufacturability, power density, energy density. And all of those come with certain sacrifices. For example, we can make the battery very, very stable by choosing the very large particles and increasing the cathode anode spacing. That's relatively straightforward. Such a battery will have a very good energy density, but the power density would be very low. It will not be able to give it out. At the same time, if we make the battery with the very high power density, first of all, it would be expensive. And secondly, it would be potentially dangerous and prone to the thermal runaway. So all of these parameters come with some complex mutual dependencies. And secondly, when we make the decisions about what to do, we actually need to incorporate the data from multiple sources. For example, if I want to make any material, I need to weight the simple theory or something that is almost an intuition. I need to use the information that I can derive rapidly from combinatorial libraries. I need to find a way to use the density functional simulation, because it may be the case that somebody has already simulated the properties of the material that I'm interested in. And of course, I need to be careful, because Combi library is cheap and real material, but that's not exactly manufactured the same way that material that I'm interested in. And of course, density functional simulation can be useful for some descriptors of the material, but we are not going to be able to predict what is the actual defect chemistry within the material. So the decisions in the real world are always very complicated. So let's look at some of them step by step and start with the case where we are interested in multiple functionalities at the same time. So in this case, let's say we want to optimize the battery, but there are multiple aspects of the figure of merit that we're interested in. So the next part of the tutorial that I'm going to show has been developed by my colleague Arpan Biswas. So he was a postdoc working with me and Maxim Ziadinov. Well, both of us were at Oak Ridge. Now he is a research professor at UTK. So what we have been working on together for almost 4 years by now. So basically, what he did was develop the framework and tutorials for the multi-objective Bayesian optimization. So what is it? Remember that in the simple Bayesian optimization, we have one objective function that we want to either discover or maximize. But there are many scenarios when we want to discover the multiple objective at the same time. So how is it different from just discovering one property separately from the other property? The answer is that in this case, we need to introduce the concept of so-called the Pareto frontier. So imagine that we are interested in the hybrid perovskite material, and imagine that we are interested only in two characteristics. So characteristic number one is the photoluminescent intensity. Characteristic number two, stability. If we explore some combinatorial space which contains multiple kind of versions of the same material, we can measure the PL intensity and stability for each point in this combinatorial space. If we take all our discovered materials and plot them in the space corresponding to our objectives, so stability and intensity, then you will see that for some materials, we can find the compositions which are better both in terms of intensity and better in terms of stability. But there are compositions that are sitting on the outside envelope of this distribution. And these are the compositions for which we can find a higher stability. But if we find a higher stability, then the PL intensity would be lower. Or we can find a higher PL intensity, but then the stability would be lower. So the points that form this outer envelope of the distribution in the stability and PL intensity space is called the Pareto frontier. So basically, these are the points that allow for optimal combination of the properties. For the purpose of the real optimization, of course, at some point we will need to choose whether we like this material or this material. But the point of the multi-objective optimization is to discover the Pareto frontiers for our objective functions rather than find the specific point. Because if we find this Pareto frontier, that allows us to make the informed decisions. So how are we going to do that? So the idea is that we need to somehow create the multi-output Gaussian process when we have the Gaussian process that generates two different functions. And then we need to somehow learn how to discover these Pareto frontiers. So the mathematics behind it is fairly complicated, so we are not going to go in it into the details. So much like we have the acquisition functions for normal Bayesian optimization, we have the acquisition function for the multi-objective Bayesian optimization. So for example, if this is our first iteration and this is the ideal solution in our parameter space, we somehow can explore the posteriori approach for the hypervolume formed by the points. So in this case, the weights are not specifically defined. The second way we can use it is the priori approach, where we calculate the perspective functions in the multi-objective space, and then we start to calculate the hypervolume in this objective parameter space. So this is fairly complicated. So the important thing to know is the names of the acquisition functions. So if you need this then it will take quite a while to figure out what they mean and how they work. Practically, for multi-objective optimization, it's already better to use the created frameworks and look and sort of explore what happens under the hood. So let me show you two examples. So imagine that this is our parameter space. We have x and y changing from 0 to 1. And we have two functions. So function 1 is very simple slope in one direction. Function number 2 is a little bit more complicated. So this is how the building the Pareto frontier using the multi-objective optimization looks like. So we can keep track of two trajectories. One trajectory is the trajectory in the design space, meaning this x1 and this is x2. So you can see how the exploration actually proceeds depending on our parameters. And you can see how we discover the points in the real space that actually belong to the Pareto frontier. So if we want to optimize this function, then it tells us that the best combination somehow are sitting somewhere here, and it explores other points as well. So this is the example of how it looks like when we build the Pareto frontier in the objective space. So in the objective space, our axis is the value of function f1 and f2. So basically what the Pareto frontier tries to do is to find all the points in the real space, x1 and x2, that correspond to the maximum combination, optimal combination of the values of the function f1 and f2. So as the result, we get something like this, and then we can show that all these points correspond to this optimal combination. So we don't have any part of the parameter space where the function f1 and f2 would correspond to this value. We have plenty of the combination of f1 and f2 when the points are here, but we are not interested in them. So Pareto frontier just tries to find out the outer envelope of all the possible combinations. So obviously, in the case when the function is two-dimensional, we can find them by direct enumeration. It's not terribly difficult in this case. But the idea is to illustrate how the algorithm works, because multi-objective optimization can work in much higher dimensional spaces. So this is a slightly more complex example. So in this case, one function is the essentially a kind of function which is lower in the this point with the 6 minima over here and the high values over here, so-called the 6-hump camelback function. The second function is the Oakley function, which has multiple optima, metastable optima, which are well separated. So in this case, the exploration of the Pareto space is a little bit more complicated. So you can see how the process happens over the design space. So we explore the different points in the real space corresponding to the function. And this is how the Pareto frontier is constructed if we give enough time for the algorithm to actually build it. So if we look at the output, in the end, we are going to find something like this. So this is our Pareto frontiers for the first example. This is our Pareto frontier for the second example. Basically, the algorithm for two simple two-dimensional functions was able to discover what are the possible optimal combinations of the properties between the two. And what you see here is the different examples of the different ways to actually acquire this property. So this is a technical detail of how it is done. So practically, if you choose the any commercial or any available libraries, that either this QEHVF function or QParigo function, these are usually the ones that are most available. So let me show you an example when the multi-objective optimization is useful. So remember that when we talk about using the Bayesian optimization for the real-world problem, the most complex thing is to come up with a suitable reward. And sometimes this reward can be non-obvious and take certain amount of time and effort to actually develop properly. However, once the reward function is created, then the problem that used to be exceptionally complicated becomes very, very simple and almost elementary. And secondly, the solution becomes traceable and explainable to a very large extent. So let's look at the example when we try to use the multi-objective Bayesian optimization to perform the task of the first image segmentation and second discovery of the radiation damage in this material. So what you're looking at in this case is the high-resolution electron microscopy image of the yttrium barium copper oxide material. So this is a classical superconductor. Before imaging, this material was exposed to the radiation. You can notice it that in some regions you can clearly see the atoms on this sublattice, and in other regions you cannot. So the radiation damage in this case doesn't make it truly amorphous. It actually kind of causes the mixing only on one of the sublattice. So the question for us becomes, how can we find all the atoms on this image? And the slightly more tricky problem is how do we find the regions where there is an amorphization? So human eye can detect them if you look at this data long enough and if you have the good monitor. But there is the thing that the human eyes are generally very well developed. So there is a good evolutionary reasons why the good eyesight was highly conducive to the long-term survival. So human's eye can notice exceptionally small variation in the images. So can we somehow use machine learning to do that? That's actually a fairly complicated task. So generally, if we want to find all the atoms, the foolproof approach to do that is to use the deep learning network. So we create the labeled examples when we say this is atom, this is not atom. Then we train the network, and then we apply the network for the whole image. So in this case, what we do is we make it a supervised problem where the neural network is basically trained from human example. And once it trained from human example, it can solve similar problems, but in much larger volumes. So the question is, can we do it differently? And for finding atoms, there are ways to do it relatively straightforward. After all, atom is just a blob. There are great techniques in the classical scikit image, for example, Laplacian of Gaussian, which is a special type of filter that finds blobs in the images. The problem with this Laplacian of the Gaussian is that, strictly speaking, it has 4 control parameters. So it has the position. So this is how the Laplacian of Gaussian roughly looks like. So there are parameters overlap that we allow to have between them, threshold parameter, sigma min and sigma max. So they are very easy to define in this image. And if we want to apply the Laplacian of Gaussian to find all the atoms in this image, we need to tune these parameters just right. If we tune them a little bit off, then we will either miss atoms or we will find the false atom somewhere. So notice that it is possible to do that. It just takes quite a while in order to tune them correctly. The problem can become even more complicated because in some cases we can use the different forms of smoothing for the image before we do that. And depending on what type of smoothing we use, the parameters of the Laplacian of the Gaussian should be different. So that's a very standard problem. So probably millions of scientists worldwide who work with the images are using this type of function. And all of them try to tune these parameters manually. And then they use the human eye to say that, hey, this approach worked. There is nothing wrong about it. Question becomes, can we cast this problem as the Bayesian optimization problem? Specifically, can we use the algorithm to use the optimization in order to find the parameters sigma min, sigma max, threshold, and overlap in the optimal way? And the optimum can be very different for different images. So what do we need to do that? And that is exactly the case where our key task is actually to define our objective function. So how do we judge that the image is correct? One way to do that is basically say that, you know what, this is an atomically resolved image. Atomically resolved image means that we are looking at the crystalline material, and if we look at the crystalline material, we know how many atoms should be there within our field of view, which basically means that we can create our objective function as the number of atoms in the image, or more specifically, the difference between this number of atoms that we found and this prediction. This is a good matrix, but that's not enough, because if we introduce only the matrix of let's find the right number of atoms, or let's find the maximum number of atoms, then the analysis can go wrong. So if we specify the right number of atoms, we will we basically will accomplish the number of positive errors and negative errors being equal, but we are not going to minimize the number of errors overall. If we specify the maximize the number of atoms, then we will basically push the algorithm to find false atoms as much as possible. So what we can do is, in order to compensate for that behavior, we can introduce the additional criteria. For example, if we find atoms, we also want to minimize the number of atoms that has distances to their neighbors smaller than some critical value. So in crystalline material, the atoms cannot be too close, because then it goes to be unphysical. Which basically means that if we introduce this type of reward function, we immediately cast our problem of finding atoms using the log function as the multi-objective Bayesian optimization problem. And this is the case where all we have to do is to take our image, we need to create our reward function based on the number of atoms we found, and the second reward function based on the relative errors. And then what we have to do is to solve this as the multi-objective Bayesian optimization problem. So we find the Pareto frontier in the space corresponding to the first and second objective function. And then there are criteria of using the Chebyshev estimate to find the point that we believe represents the local optimum on this Pareto frontier. So what does it mean? It means that if we take a fairly common analysis function that quite a lot of people use, and if we make it a part of the Bayesian optimization with the physics-defined reward, then we have the algorithm, which is very, very fast. And we can, of course, benchmark it against the neural network. So the well-trained neural network finds all the atoms. Turns out that the optimized log algorithm also finds all the atoms, including the visible ones and poorly visible ones. What's even more interesting is that if we try to estimate how well the Laplace of the Gaussian method behaves if we start to add noise to the image, and then we try to do the same thing for the neural network. So this is how the neural network behaves if we start to add just simple random noise. So above certain critical level of the noise, the network start to interpret a lot of locations in the image like false atoms that were never there. You can see that at this noise level, it has found a lot of extra atoms in the wrong location. So the total number of the atoms found as a function of the noise level goes up. You can see that our relative error so goes from 120 to 240. Once we run the same type of algorithm with the log, it basically gives the behavior which is for this noise level is actually much better than the neural network, simply because it tries to find the atoms, but it also penalizes the scenarios where the atoms are too close to each other. So the neural network will find atom close because it can. In our case, with the optimization workflow, we actually penalize it. So it's actually behaving much better than the neural network. And the most important thing is that neural network is actually a supervised approach. So we have to train it. And it's not only a supervised approach, it's also computationally intensive approach. So generally speaking, deploying the neural network takes a lot of time and effort. Optimization loop on the log is easier. Not super easy, but much, much lighter. So what about more complex problems? So I mentioned that maybe we also want to find the region where there is this radiation damage. And look, for human eye, these regions are fairly obvious. So we can see that here there is a damage, and here there is no damage. Problem is that the human eye and human attention is limited to relatively small parts of the sample. So the question becomes, can we somehow find it in a more automated way? So the typical simple strategy would be to do the human labeling of the regions where there are damage and then there is no damage, and then try to use the neural network as the classifier to say that there is damage here, there is no damage here. So for this particular sample, this approach didn't work. And of course, if you talk to the people in the computer science community, they always will tell you that if something didn't work, that means that we need to have more data. And that's true. But the problem with the more data in the experimental setting is that for supervised machine learning, the data has to be labeled. And labeling doesn't come from nowhere. It's actually your time or time of your group. Question, it's always better try to use the unsupervised methods or the weakly supervised method. How would we do that? So the typical workflow for data analysis in this case is to take the image, find and classify all the atoms. So in this case, you can see that all atomic species now have a different label shown by color. And then using this found atom as the anchor points, come up with some dimensionality reduction or classification algorithm that will allow us to see the difference between the amorphous and non-amorphous layers. It is possible to do that. So if we spend enough time essentially playing the Lego game, trying to play with the different descriptors, different transforms, different dimensionality reduction methods, after a while, we can easily find the representation like this. So this is a variational autoencoder as the nonlinear dimensionality reduction method that clearly shows that some of the regions are different than others. Okay, that's good. The problem with this approach that it is, first of all, it takes a lot of time. Secondly, it is non-myopic, meaning that if I change the parameters of my descriptors here, it will affect my analysis at this stage, and it's difficult for me to figure out how. And most importantly, depending on who the operator is, the answer would be different because you get the plausible answers for multiple ways and multiple parameters involved in this workflow. So the question is, can we make it traceable, and can we make this pipeline fully automated? The answer is yes. We can do that if we do two things. The first thing, we define the reward function that allows us to judge that our analysis was successful. And that's a difficult part or non-obvious part. And the second part, we cast the whole workflow as the Bayesian optimization in the combined parameter space of the system. So for example, our parameter space has two dimensionalities coming from the size and shape of descriptor. There is another dimensionality. There is a discrete component coming from what transform we use. And then there are additional discrete or continuous components based on what dimensionality reduction method we use. So in this case, it's a hybrid problem. Some of the dimensions are categorical, like this can be categorical, or the choice of the covariant function in GMM is categorical. Some of them are continuous. But the interesting thing is that if we follow relatively simple physical logic, then it works remarkably well. So it turns out that all we have to do is to, okay, we already know where the atoms are. So the first thing we need to do is to classify the atoms. The easiest way to do that is to define the patch around the atom and then do the Gaussian mixture model classification. So lo and behold, all the atoms in the image form 4 different groups. So notice one tricky thing here, that this is the representation in the two-dimensional space, so in the space of the principal component. Practically, the GMM clustering happens in the very high-dimensional space of our patches. So if our patch is 30 by 30 pixels, that means that we are doing clustering in the 900-dimensional spaces. So this is just an optimal representation. So we can separate all the atom types. We can choose to focus only on on the barium atoms. So practically, there are two types of barium atoms because the barium atom on the top layer and the bottom layer are different. So we don't have the symmetry in the analysis. So let's assume that we want to identify all the amorphous regions if we choose at the anchor points only the barium atoms in the top layers. And then if we try to separate those atoms, we see that there is some distribution, but there are no longer two obvious groups. So in this case, four obvious groups are obvious because these are different crystallographical positions. They are very different. So in this case, we have two groups because the barium atom at the top of the layer has different neighborhood rotated by 180 degrees compared to the one on the bottom layer. So we also have two groups. But now when we are stuck with just one type of the barium atoms, in this case, you can see that there is some structure to this distribution. So there is one part of it, there is a second part of it, but there is no clear definition. Again, remember that this is a clustering in the 900-dimensional spaces. So what can we do? And it turns out that in this case, the approach based on the reward function again works remarkably well. So what we need to do is to define our analysis workflow as an optimization problem. And in this case, the optimization parameter space is the size of the window where we build descriptors. It is a few other elements of the workflow, but ultimately, this is the parameter of the Gaussian mixture model. So in this case, we have a threshold. So in all classification problems, we can shift the threshold corresponding to the decision, and it is a covariance type. So we can cast this problem as the optimization problem corresponding to this fairly, I mean, it's not super large, it's maybe a four-dimensional, and then one dimension is the covariance type parameter space. And the interesting thing that it works, but we need to define the reward functions. So it turns out that in this case, the natural reward functions are the compactness of the amorphous region. So we believe that the radiation damage should be concentrated in some region and don't form structures like a snowflake or something like this. And second optimization function is the perimeter. So we think that we should balance the classification with the sort of having the perimeter of the damaged regions being relatively small. Once we introduce these reward functions, we can cast our problem as the optimization problem. And lo and behold, this is the representation of the decision boundary in this case. And these are the amorphous regions that we have found. So you can say that, you know what, these objectives may be somewhat questionable, so it is possible to come with others. So what is going to happen if we have a different objective? The answer is we will plug it in the same workflow. But what if we say that we have more than two objectives? Well, that's exactly why we have multi-objective Bayesian optimization. So we can easily solve the same problem with the multiple additional objectives. And the interesting thing is that if the objectives are not conflicting to each other, so they all lead us to the same answer, then they are not going to conflict. We are going to get the same answer. So that's actually kind of interesting. And this example illustrates that the multi-objective optimization can be applied to the real-world problems and sometimes in a fairly non-trivial ways. So let me show you another example of the multi-objective optimization where we try to understand the properties of the ferroelectric material. So in this case, we work with a scenario where we have a ferroelectric material. Ferroelectric material is sitting on the bottom electrode, but on the top of it, there is a water layer. And it turns out that there is a fairly complex interaction between the polarization inside the material and the electrochemical properties on the surface layers. So what we can do is we can solve this problem numerically, so that requires a lot of computation. And then we get the answers in the form of the essentially parameter behaviors where we have the characteristic hysteresis loop as the function of, let's say, pressure and temperature. So this is the example where you can see that there is a part of this parameter space occupied by the classical hysteresis loops. There are parts which looks almost like paraelectric. There are parts that look like antiferroelectric. So why is it interesting? It is interesting because these materials can be used for either energy storage. So the energy storage is essentially given by the open part of the hysteresis loop, or by the information storage. So the question becomes, how can we navigate these parameter spaces of this model, and presumably the real materials once we actually make them, in order to find the parts of the parameter space where there is the best storage properties versus where there is a better information storage. And again, this is the case where we can use the multi-objective optimization, but in this case, we have to spend tremendous amount of time building our reward function. We cannot just explore the parameter spaces looking for different behavior of the hysteresis loops. This is not a very well-defined problem. What we need to do is to go through a very long slog where we first start with the classifiers of our hysteresis loop. We need to introduce the cases when there is one or two loops, and then we need to figure out how to calculate the total energy and energy losses, so the parameters that we're interested in. So in this case, the problem starts with building the decision tree reward function. But again, once it is built, then we can use the decision tree reward function in order to explore our parameter space. So developing of the workflow like this is remarkably time consuming. So it actually will take maybe a month to build it, even if you have the access to the model, because there are a lot of moving parts to that. However, once it's done, then we basically kind of cast our problem as the multi-objective optimization. So this is the example of the storage. This is the example of the loss. These are the example of the Pareto frontiers that balance the how much we can store and how much we can lose on the how much we lose during that properties. So and of course, there is a paper where you can read about it in the detail. So these are the examples of the multi-objective optimization. But there is another very important case of scenarios where we deal with more than one available model. So think about, so now we are going from multi-objective to the multi-fidelity type of problems. So they are very, very different. So multi-objective means that you have optimization over the same parameter space, and there are more than one objective that we want to optimize. So our goal is to find the Pareto frontier between these properties. Multi-fidelity problems is the simplest example of the scenario where we can measure more than one thing. And so we have expensive model and cheap model. So the expensive model is more accurate, but it's expensive. Cheap model is less accurate, but it's cheap. So the question becomes, can we use the less accurate cheap model to help us make a better decision for the expensive model? And that's exactly what the multi-fidelity Gaussian processes are for. So the examples where they can be encountered in the real world scenarios is very straightforward. For example, if we work with the combinatorial libraries of the deposited by this compositional spread approach, they encode all the physics of the material. However, if we want to access it using the electron microscopy measurements are very expensive. So it takes weeks to make the sample, image them on the microscope, analyze the data. So the question becomes, can we use a cheaper measurements, for example, when we measure topography or the piezo response properties across the combinatorial library, in order to help us select the locations for the electron microscopy measurement? Very practical question. Another example is that whether we run the AFM experiment, where the AFM experiment is expensive, can we use the computations in order to help us figure out where on the combinatorial library we can look at? Because the property of the combinatorial library, in principle, are determined by some form of the Ginzburg-Landau theory. So can we use the computation as the way to help us choose the locations for the measurement? And here the behavior is tricky, because if the computation could exactly reproduce the experiment, we wouldn't even need to do the experiment. So then we already know everything. The problem is that the computation can tell us something about the distribution of the properties, but this model would be imperfect. So intuitively, it is clear that we need to discover not only the low fidelity and high fidelity behavior, but we also need to find out the connection between the two. And that's what is called the fidelity kernel. Of course, there can be more complex fidelity cycles. For example, if we use the combinatorial libraries to study the electrochemical properties of the solid electrolytes when there is a distributional composition, we can think that scanning probe microscopy can be a very low fidelity measurement that's fast and relatively cheap. Measuring impedance spectroscopy can be a medium fidelity, choosing the composition and measuring property on the bulk composition is the high fidelity. So there can be multiple levels, and the framework that can work for 2 will work for 3 as well. So how can we do that? So let me show you a little bit of example first in the PowerPoint, and then we are going to switch to the notebook where the multi-fidelity measurements are discussed in more detail. So generally, what we do is we assume that there is a ground truth function. So that's what we want to discover. And we also assume that there is a low fidelity approximation to the ground truth function. So our measurement can be twofold. Either we choose to do the measurement in the low fidelity space, or we choose to do the measurements in the high fidelity space. So the red curve is high fidelity, the black curve is low fidelity. We assume that there is some relationship between the low fidelity and high fidelity function. We don't know what this relationship is before the experiment. It's our goal to discover this relationship during the active learning. How it can be discovered depends very much on what model we use. So I'll show you the example of the multi-fidelity approach. It simply uses one kernel that connects the low fidelity and high fidelity space. So then the way the multi-fidelity, so as I mentioned in the beginning, multi-fidelity can refer both to the type of the Gaussian process, and it can also refer to the type of the problem. So multi-fidelity GP uses a single kernel that connects the low and high fidelity spaces. If we have more than 2, then it becomes a matrix. So then the way that the process goes is that we can take measurements either from low fidelity space or high fidelity space. Our algorithm tells us what should we measure next. So that part is tricky. We'll get to it in a second. And it tells us, and it tries to reconstruct the mean function for the low fidelity, mean function for the high fidelity, and it builds the uncertainty intervals for both of them. And it obviously tries to reconstruct what is the multi-fidelity kernel that connects the two. So in our implementation, we use the fidelity kernel that looks something like this. So it basically says that there is some exponentially decaying correlation between the two spaces. So what we try to learn is the single parameter that determines the strength of this coupling. So if this parameter is very, very large, that means that the low fidelity space and high fidelity space are not connected. There is no connection between them. So exploring one would not help us explore the other one. And therefore, if we want to learn anything, we just should explore the high fidelity space. If this parameter is vice versa very small, that means that the low fidelity and high fidelity space are closely coupled, which means that the low fidelity measurements are almost as reliable as the high fidelity. Obviously, in this case, we don't need to use the multi-fidelity approach at all. We can just find the run the low fidelity method. But it's a learnable parameter. So before the experiment, we don't even know. Now, the very, very tricky part here is the choice of the acquisition function. So remember that the Gaussian process does only the prediction and gives you the prediction and uncertainty. So if we have this many measurements in the low dimensional space, this many measurements in the high dimensional space, in the high fidelity space, sorry, the multi-fidelity Gaussian process, and given the kind of kernel parameters in one space, second space, and coupling, the multi-fidelity Gaussian process will predict the low fidelity function everywhere, and it will predict its uncertainty. It will predict the high fidelity function everywhere, and it will predict its uncertainty. And then it is up to you how to choose where to take the next measurement. So as you remember, for simple Bayesian optimization, there are multiple ways how we can choose the acquisition functions. So as you can imagine, for the multi-fidelity problems, the number of the ways of how we can choose the acquisition functions is even larger. So for the time being, the best advice I can say is to either use the well-established frameworks and try them first, or construct the acquisition function based on the real cost and real values of your measurements. So if your cost of the measurement is known, it's very straightforward to add it to the multi-fidelity framework. If the value gain is known, then we are comparing apples to apples. In all other cases, we need to experiment. So this is how I'll show you how it has been realized. So in this case, we say that low fidelity measurements are simply cheaper than the high fidelity by the factor of C. And the cases where we use it for example, using the, imagine that you run a theoretical simulation or where the parameter that matters is the size of your model. For example, you want to explore the properties of the Ising model. So if you have a 20 by 20 field and 100 by 100, 100 by 100 gives you more correct answer, but it's more expensive. 20 by 20 is easier to calculate. But in all cases, but we know very well what's the difference in terms of the computational complexity, and that becomes our cost. If we synthesize the materials in the lab, then we know very well what's the cost in terms of time and money for the spread library versus the single composition. So we can use that as a cost. So anyway, these are the few examples of how the multi-fidelity approaches work. So we create our acquisition functions for the low fidelity and high fidelity acquired, adjusted by the cost. And then we do the measurement for whatever one is the argmax of the more complex, of the more expensive of those functions. So we choose between the two. That's how this algorithm by the Shu and Yang or Wang works. So these are a few iterations. Let me show you let me show you the notebook where it's realized. But just as an example, these are the few cases where we have low fidelity and the high fidelity solutions. So let's look at the notebook that explains how it is going to work in real time, in real life. So let me switch to the notebook. Okay, here we are. Did I share the screen? No, I didn't share the screen. Here we are. So this is the notebook that has been developed by Arpan about a year ago that introduces the multi-fidelity approach. So it should be on the GitHub. So let me know if you don't see it and don't have access to it. So let's look at what goes on here. And we'll spend considerable amount of time with that because here all the details are important, both in terms of understanding of how to use it and in terms of what it can do and what it cannot do. So the thing about this notebook is that it is developed to cover both the standard BO and multi-fidelity BO and introduce the structured multi-fidelity Bayesian optimization. So that one is, as far as I know, is fairly unusual. So I haven't seen the implementation of this type of algorithms before. And under some cases, it can be very useful. So structured methods which introduce the partial knowledge of physics actually make life easier. But it also brings some very interesting and unusual balance in the multi-fidelity approach. And the difference is that if we introduce the structured mean function, that means that we postulate some knowledge about the physics of the system. If we introduce multi-fidelity approach, that means that we trust the cheap measurements to tell us something about more expensive measurements. These two things both come with a certain degree of belief. So we either believe in physics completely or we believe in data completely. So practically, it turns out that we can have a situation where at some point the data part of it tries to bring us in one direction, and the physics part tries to navigate us in slightly different direction, which will mean that at some point we'll have to choose which one to trust more. So point is that once we are going for the problems such as multi-fidelity and multitask problems, they implicitly have a lot of domain knowledge beside them formulated as the belief in either data or the prior knowledge of physics. And it's very important to understand where these parameters come into the model and how to balance them when we use the model. So let's look at the beginning. So this is our standard installs and the imports. So after that, we define the objective function and the approximate objective function. So in this case, the objective function is just a Forrestal function. And the approximate objective function is the Forrestal function, which is tilted by a small slope and there is some offset. So basically, these are very, very simple functions, which we, as usual, use to illustrate the concept in 1D. We define the boundaries of the interval that we care about. We define the sampling interval. And lo and behold, once we plot it, we have our ground truth function. So this is what we want to discover. This is our expensive measurement. And this is our low fidelity approximation. So in other words, we want to understand, either optimize or discover this red curve, but the red measurements are difficult. So the dotted black curve provides our low fidelity approximation. Now, here comes the interesting part. So we need, in this case, our fidelity kernels are specified explicitly, so we see what happens inside. We, of course, can hide them behind the hood, and then we will never know. But this is what it has. So the fidelity kernel has k lengths as before, k scale, so the length scale of the correlation and the vertical scale. And then in the simplest case, it also has this parameter delta, which defines the correlation between the kernels for one function and another function. And then our total kernel is basically defined in this way. So this is our fidelity kernel. It's defined as the delta times the difference between the x fidelity and z fidelity. So the total kernel for multi-fidelity process is basically the spatial correlation kernel, the usual RBF, and the fidelity kernel. So once we multiply them, we have the kernel that defines the correlation between the points and x space. So from one point to another, much like the normal kernel in the simple Gaussian process, and the kernel that defines the correlation from the low fidelity to high fidelity. So this is relatively simple concept. So in some sense, it's just the direct expansion of the concept of the classical kernel in the Gaussian process. So then we also need to define the acquisition function, because once we are going from Gaussian process to Bayesian optimization, we need to make decisions. And in order to make decisions, we need to define what is that we are looking for, how we balance the prediction. So remember that we will predict the low fidelity function, high fidelity function, the uncertainties. We need to make decisions based on those. So the way that we are doing it here is basically create the acquisition function for the high fidelity and the low fidelity function. And then we create this combined acquisition function as shown in that paper. But again, it can be defined in any way that you want. It depends what are the real cost of the experiment and the data. Once these are defined, then everything else becomes the usual bookkeeping during the Bayesian optimization. We choose what the next location to measure. We take the point from there. We plot the answers. So let's see how it works. So this is the example when we start to run the classical Bayesian optimization. So we introduce our parameters, we introduce the train bounds, we run this is our initial optimization, this is our initial observations. So we run the Bayesian optimization, this is what we are going to see. So this discovery loop is something that you already have seen many, many times. We introduce what is our experimental budget. We introduce the control parameters, then we start the optimization loop, and then we do the usual Gaussian process magic. So we create the exact Gaussian process model with the one-dimensional parameter space, with the RBF kernel. We fit the model to our data. Then we check the prediction. So this is done here every 5 times. We compute our acquisition function. Once we calculate our acquisition function, we choose the argmax. This is where we take the next measurement. If you're interested, we can always choose a different acquisition function. So this is expected improvement, but it can be UCB. Then we plot the results. So let's see how it worked. So this is where we started. So the red curve is our ground truth. The green squares are our observations. What we get is the high fidelity mean, and we have the uncertainty interval. So in this case, the behavior of the function is something that you're already familiar with. So we can see that in the points where we took the measurement, it tries to approach the measurement. Notice that our noise prior makes for deviation between the measurement and the position. And you can see that in the locations where there are no measurement, the function kind of reverts to 0 because this is a 0 mean. So in this case, we chose the classical 0 mean function. And then if we keep running the experiment, we are going to update the function. We are going to update the uncertainty. You start to see that we start to have a more familiar behavior. So if the uncertainties look like this, that means that our kernel length becomes comparable to the distance between the measured points. And let's not discuss it step by step, but lo and behold, we are going to find that our measurements converge in this and these locations. So notice that it is very unwilling to explore this location. There is a high uncertainty here, but not sufficiently high to justify us exploring this maximum. So in some sense, if we run the simple Bayesian optimization without the low fidelity data, we found this maximum, we found this maximum. We did not find this maximum simply because we got unlucky. 2 of our measurements ended up being on the minima. There is no reason for the algorithm to even suspect that there is a maximum over here. If we make the strategy more exploratory, we will of course eventually find it because the uncertainties here and here are small. And for more exploratory algorithm, we will do the measurement of this location. But for the chosen acquisition function, it didn't happen. So we were too greedy. Greedy algorithms get trapped. Let's run the same thing as the multi-fidelity optimization. So in this case, the setting of the problem is a little bit more complicated. So we need to define the initial seed points. And of course, we need to define the initial fidelity values as well, because we need to initialize our fidelity kernel. So now this is how our ground truth is going to look like. So we have ground truth behavior, the red curve. So this is what we want to discover. We have the low fidelity approximation. So this is something that can help us discover the red behavior. And we can do the measurements either in the low fidelity space when it is the purple process, or in the high fidelity space. So we assume that these measurements are cheaper, but at the same time, it's not what we are ultimately interested in. There is just a correlation between the purple measurements and yellow measurement, but we want to discover it. And once we discover it, it will help us find where is the maximum for the red curve. So let's see how it goes. So in this case, we again define this Bayesian optimization loop, and we run the results. So in this case, we already have two acquisitions. So notice that our outputs changed. So now we have the delta. So delta tells us how strong the algorithm believes is the correlation between the low and high fidelity measurements. So other than that, there is the standard kernel parameters in terms of length, scale, and noise. We assume that they are the same. So it's the same kernel for low and high fidelity. The only difference between them is the correlation caused by delta. So as I said, this is the easiest way to introduce the multi-fidelity process. So then when the algorithm runs, we are going to observe multiple outputs at the same time. So we always show the ground truth and the low fidelity approximation. So both of them are hidden. Algorithm needs to learn them. We show the mean for the high fidelity and low fidelity. So this is our surrogate models. We have uncertainty intervals, and we have the observations. We also generate the acquisition functions. So we select the acquisition function for low fidelity and high fidelity. The high fidelity one is adjusted by the cost, and then we do the measurement in the one which is argmax. So you can clearly see that in this case, we have the measurement here. So somehow the acquisition function is maximum for the high fidelity measurement in this part of the parameter space. So once we do that, we take the measurement, we update everything. We update the delta, and we update the kernel parameters and noise. So notice that delta increased. So in this case, the algorithm believes that there is a correlation between high and low fidelity is higher. So it recalculates the high fidelity mean and low fidelity mean, and recalculates the uncertainties. Notice that the kernel length is fairly small. So this part is completely unexplored. So the algorithm thinks that in this case, the value of the function is 0. So we recalculate the acquisition function. Again, we want to do the high fidelity measurement. We did another high fidelity measurement. So this is our update. So notice what happens from this point. So now the algorithm is absolutely certain of the high fidelity answers. So now it wants to measure the low fidelity behavior. So this is the result. We've done the measurement. So now it's even more positive that the high fidelity and low fidelity are connected. So and then we are going to kind of iterate multiple times. So we have the example of the evaluation of the acquisition function for the high and low fidelity. So if we see the process, we are going to go through it over and over and over again until we, probably cannot kind of examine all the solutions, all the steps of this process. But after we are done, let's go to the end of the process. After we are done, this is what we are going to get. So notice that in this case, the knowledge of the low fidelity function actually helped us discover the true maximum of the high fidelity function over here. And the reason for that was that we've been very exploratory about the low fidelity data set, and the presence of the correlations between the low fidelity and the high fidelity suggested the algorithm that there, in fact, can be a maximum over here. And therefore, it did the measurement and discovered this maximum. So obviously, as you can imagine, we spent some time tuning this example, but that's the idea of the multi-fidelity approaches. That's what they ultimately try to do. So now let's look at the second example, which is the multi-fidelity Bayesian optimization with the structured Gaussian process. So in this case, we again define the low fidelity and high fidelity function, but the difference will be that our ground truth function, so the high fidelity function, will have a jump. And the low fidelity function is going to be just a function like that. So that's a little bit closer to the type of problems that we encounter in the real world situation. So for example, the real system can have a behavior which is slightly different in some important detail from the approximation or theory that we use. So let's see how we can use the multi-fidelity approach for this type of scenario. So let's start with the just creation of the random seeds and the random observation. So this is what we get. So we created the random, more or less randomly chosen these locations to do the high fidelity measurement. We've chosen these locations to do the low fidelity measurements. So let's see how it is going to work all together. So let's start with the standard multi-fidelity Gaussian process, where the Gaussian process itself does not have any prior knowledge. So how do we do that? We create our model. We defined already fidelity kernel and fidelity kernel priors. So this is nothing else. This is the usual discovery loop. So this is what we get. So in this case, it's kind of useful to see what is going to happen between the reconstructed functions and how they're going to accommodate the changes in the system. So first of all, we start with the observation in the low and high fidelity space. And first we build the Gaussian model that tries to judge the strengths of connection between them and tries to build the kernel in the real space. So as you can see, in this case, we start with a very poor approximation. So our high fidelity and low fidelity means are both almost zero pretty much everywhere. Our kernel length is very small, which basically means that the algorithm thinks that it can trust the measurement, but it cannot extend far from those measurements. So we don't know what goes on here. It's uncertain. So in those cases, the acquisition function basically say, you know what, we know something in those locations. These are the locations that we don't know anything, so they're equally important for us. However, this location is more interesting than the other because here there is a small chance that the function is actually higher. Why would it say that? Look at these yellow points. So this yellow point is, relatively speaking, highest than the other four, which basically means that if we have the optimization problem, then this would be the first point where the measurements are taken. It's not a huge preference. So this is how much the lack of knowledge matters. This is how much being close to the answer matters. So we do the calculation, we do the measurement, we recalculate our parameters of the multi-fidelity process. Then we want to make sure that our low fidelity function here is also high because we want to find out what the value of the fidelity kernel is, how much we can trust it. Lo and behold, what happens at this stage is that the algorithm was able to learn only from this location how much it can trust low and high fidelity measurements. So notice what happens here. Delta is 0.86. So if delta is 0.86, that means that, remember that the kernel is minus delta times the difference. So here, the delta become much larger. So after we done this measurement, it becomes 3, which basically means that all of a sudden the algorithm start to treat the low fidelity and high fidelity measurements separately. They are now weakly related. But at the same time, it start to trust the correlations in space. So all of a sudden, our kernel length stop being 1/10, it becomes 5/10. So now there is no, the algorithm thinks that there is no grand unknown outside of the measurement points. In fact, we have a way to calculate the acquisition functions across our parameter space that are almost reasonable. And then we start to iterate this process. So you can see how the cost-adjusted acquisition function for high and low fidelity look like. So now the process start to look considerably better. So notice interesting things. So kind of notice what happened here. So we've chosen in the beginning, we chosen the observations, chose the high fidelity curve to be considerably higher than the low fidelity. So notice that the algorithm have done measurement here and here. It observed that the answers are very different. So you see that the high fidelity mean goes like this, low fidelity mean goes like this. And based on that, it made the decision that these are very different functions and they're not that connected to each other. So that's not entirely right, of course, because they have a lot of similarity, but algorithm doesn't know that. It makes the decision based on only of the observation that it has in hand. And the system is actually fairly complicated. But once it starts to do measurements at this locations and this location, it starts to come to conclusion that maybe this point was an anomaly. Maybe throughout the whole parameter space, the correlations between the low and high fidelity functions are in fact very higher. And what we are going to see throughout this process is how the algorithm tries to tune the delta, how it tries to tune the kernel lengths in order to figure out what in fact is going on. So same type of logic kind of applies if we go through the rest of this optimization loop and see what we are starting to converge to. So we are starting to get to the point where the algorithm, remember that we are trying to solve the optimization problem. We want to find the red maximum. And we explore everything because we think that the maximum can be anywhere, not necessarily in the ground truth location. So if we go through the algorithm for quite some time, you will see that sometimes we go back to the situation where nothing is known. So algorithm lost confidence in the correlation between the low and high fidelity function. But in the end, that's what we get. So what happened? So this is a classical behavior when we have the multi-fidelity process, when we have the Gaussian process, when there is a sharp features. So the algorithm has done measurement around this location. It kind of sort of was able to discover the place where the maximum is. It tried to do its best to find the high frequency mean and say that this is a maximum. So you see how it goes. But the price for finding this maximum is the lack of knowledge for everything everywhere else in the parameter space. The Gaussian process, by definition, thinks that it knows what goes on the length scale compared to the kernel length. So if we have a sharp feature and we discover these sharp features, that means that this knowledge, this extent is actually very, very small. So you can see that in most places, our high fidelity and low fidelity means reverted to zero. And that means that the algorithm simply doesn't trust itself. It basically gives us an estimate how many additional measurements we need. And we can get this estimate if we divide 10 by essentially 3 times the key length. So that's not the best situation. So why did it happen? It happened because we have a jump, we have discovered the jump, and the algorithm has no way to know that there is just a single jump in the system. So can we do better? And we can do better if we somehow introduce the knowledge that there can be a jump in the system. So the way that we do that is we introduce the probabilistic model for our mean function. So the way that we introduce this probabilistic model is in this case, we choose the model that is simply the ground truth model, but it will work reasonably well even if the model just accounts for jump, but doesn't have the exactly correct shape corresponding to the rest of the function. So we define the mean function, we define the priors on the parameters. So in this case, it is the position of the jump, which can be anywhere between 5 and 10. And it defines the values of the parameters A and B. So these are the parameters. So basically, we say that our min function is defined with respect to the vertical offset to the left of the jump point and to the right of the jump point. So this is obviously a special case, but it's relatively straightforward to define the parameters in any way that you want. It will work roughly the same. So the key thing would be the availability of the jump. So the important thing, as we discussed many times, is that the closer your probabilistic model to the actual physics of the system, the better the whole construct will work. It is important, however, to stay broad enough that our uncertainty, our flexibility of the model allows for all possible scenarios. So if our model is too prescriptive and the real behavior is different from what is covered by the model, then things will actually work rather poorly. So it's important to provide the model, but keep it flexible. So let's see how things will work in this case. So we created before our observation of the high fidelity curve, observation of the low fidelity curve, and then we define our Bayesian optimization loop. So the only difference to the one that we discovered before is the fact that we provide the min function and we provide the min function prior. So that's it. So now our Gaussian process is multi-fidelity, but it's also a structured Gaussian process, not the simple one. Everything else remains the same. So we have the same visualization functions. We have the same acquisition function. So let's see how the algorithm will behave. So this is our discovery cycle. So now our outputs are parameters A and B. So these are the vertical offsets on the left and on the right. It is the position of the jump point, T. It is the strength of the relation kernel. And these are the length scales of the normal kernel. So this is where we start. So in this case, we again show the ground truth function. We show the high fidelity and the low fidelity min functions as before. So notice that it tries to stick to the observations when it can. It shows the uncertainty intervals. So for the time being, nothing interesting. So this is our acquisition function, and and this is how the process starts to evolve. So notice an interesting thing, that once we provided the values of the function, then we have a much better behavior in the regions where where we didn't have any measurements. So remember that in the scenario when we are far from the measured points, so when our kernel length scale is still small, which means that the algorithm thinks that things are known only here and here, but nothing is known in these locations. So notice that if we run the algorithm in this way, the behaviors away from the measured points revert to the mean function. And the mean function in this case is chosen to be kind of correct. Therefore, the behavior that we observe is correct. It's not specified rigidly because it is defined down to the parameters A and B, and these parameters are learned from the experiment. But because we fix other parameters and because we use the mean function, these are the prediction in those locations. Another important thing is notice the value of the parameter t. So it is positioned here. It's actually fairly close now to the true position of the jump. So let's see what happens if we iterate the process. So if we iterate the process, our next measurement basically tries to pinpoint the position of the jump. So it's the part which gives the biggest contribution to the uncertainty. and then it tries to pinpoint what happens on the right. So after a few iterations, we actually found that the maximum of the objective function is actually accomplished. So remember that our goal is not to find the true value of the function everywhere. Our goal is to find the maximum. Once we specify the form of the mean function, that makes the search much more expensive. The caveat is that the k length in this case becomes very, very small. So the algorithm is basically completely lost the confidence in the spatial behaviors of the functions. If we keep running the experiment, then you can see that the k length starts to increase, so that it becomes broader, broader, and broader. And in this case, we believe that this is kind of goes to the point when we can start to trust our measurements. So you can see that now we have reconstructed the function remarkably well. And in the end, the process has effectively converged. So in this case, the red function is our ground truth. So the blue function is the high fidelity mean function. So notice that the blue function is fairly different from red in the parts where we really don't care that much about, but close to the maximum where we are interested in it, where we think the maximum is, it actually discovered it remarkably well. So comparatively, the low fidelity mean, so you see how it behaves. It kind of goes like this. It's explored this region remarkably well because it was suspecting that maybe this is where the maximum is. And here it is kind of so-so. It also has a jump. The jump is obviously at the same place as for the high fidelity. So they kind of use the combination of the certain amount of the low fidelity measurements and high fidelity measurements to make absolutely sure that we find the maximum. So it can be interesting to run the same algorithm when our goal is discovery. So our function is not optimization, but simple uncertainty minimization. So you're welcome to do that. It's actually fairly straightforward to change this code in order to be able to get this answer. What happens if our function is partially correct? So let's see what happens in this part of the code. So we define a different function with the jump, but in this case, we don't. So in the previous example, our function was exact. We just kind of played with the jumps. In this, we played with the offsets as the free parameter. In this case, we define the mean function that it has a jump at the parameter t, but on the left and on the right, it is just a square function, so square minus a, square minus b. So it's a very different form than this complex sinusoidal function. So what it means is that we are now running the multi-fidelity experiment with the mean function, which has some aspects of the physics that we're interested in, but only one aspect, but not the detailed behavior. So let's see what happens in this case. So we define the same, we define the similar probabilistic model. We initialize the values of the function in the high and low fidelities. We compare the results. So this is our ground truth. This is the low fidelity approximation. Let's see if having this second mean function, which is just parabolas with the jump, if it is going to help us find the high fidelity maximum. So we go through the same point. So this is same loop. So let's see what happens. So as you can imagine, this is where we start. So these are our observation of the low fidelity and high fidelity data. So this is our reconstruction curve for the high fidelity and low fidelity. So see what happens. So here we have enough points. Let's look at the low fidelity first. So we have enough points for the low fidelity data. So our reconstructed low fidelity mean behaves kind of okay. Then it starts to go like this. So why is it going like this? It's going like this because simply because we provided the prior for the mean function to be this quadratic function. And the value of b, these are our values of a and b, this is our value of the jump. So interestingly enough, it already thinks that the jump is roughly somewhere here, which is already very good. So this is how we construct the acquisition function. So we go through high fidelity, low fidelity acquisition function, see what happened here. So as we saw in the examples before, we need to look where the uncertainties are. So see what happens. This is just third step of our discovery process. The algorithm decided that the highest uncertainty is here. And the highest uncertainty is here means that this is the place where it is going to try to find the jump function, or the position of the jump. So everything else is okay. Again, look at the agreement between the red curve and the blue curve. So agreement between the red curve and blue curve tells us how the ground truth for high fidelity and how the surrogate model agree. The black curve and the orange curve tells us how the ground truth for the low fidelity and for the surrogate model agree. But the uncertainties tell us where the algorithm is likely to explore. So uncertainties is high here. Unsurprisingly, we are going to run several experiments when we focus our attention on the jump. And then lo and behold, very quickly, our algorithm actually converges and we discover the true position of the jump. So this is our, you cannot even see the difference between the blue curve and the red curve. So our high fidelity surrogate model and the ground truth by now are identical. And notice that we did both the low and high fidelity measurements to discover it. So after it is done, the algorithm is going to check what is going to happen here because there is a high prediction and high uncertainty. And then it kind of goes to explore the parameter space, and then basically that's it. So in the end, we actually were able to discover our true behavior, and we did it remarkably well. So this being said, let me show you another example of how we can solve the similar problem. And this is something that we can do with what is called the multitask Bayesian optimization. So what is multitask Bayesian optimization? Okay, let me switch to the right window. This is wrong one. Here we are. And share the screen. So multitask Bayesian optimization is a considerably more complex concept than the multi-fidelity. So if you will, multi-fidelity Bayesian optimization is a relatively simple tool where we essentially do measuring the predicting 2 for the price of 1. So we have the same kernel, we have in space, we have 2 observables. These 2 observables are correlated. We just introduce 1 parameter in order, or 1 more element to the kernel to quantify the correlation between the 2 of them. It is very useful. However, it is a very, very non-flexible tool. We essentially just have 1 parameter to connect 2 fidelities. We can play with the mean functions, but mean functions comes with a physical bias. So depending on how right and how prescriptive they are, the behavior can be totally different. So with the multitask Gaussian process, we introduce a considerably more complex model. And this model is called the linear model of the co-regionalization. So basically, it is defined. So let's first talk about what it is can be used for, and second, what happens under the hood in this model. So the type of problems that we use the multi-fidelity and the multitask Gaussian process are exactly the same problems. It's the problems when we have access to multiple sources of information and we need to choose which one to acquire. So we can use the multi-fidelity model to solve multitask problem, and we can choose multitask problem to solve multi-fidelity problem. It's only in the name. But on the level of the Gaussian process itself, the difference is actually enormous. So the multi-fidelity process has just one kernel. So multitask Gaussian process is considerably more complicated. So what it does, it uses the same concept of the latent process as the autoencoder. So each latent we define the number of the latent processes, so that's a kind of model parameter. So there are several latent processes that are under the hood. We assume that each of these latent processes is given by the Gaussian process itself. So latent process means an independent, non-observable, independent Gaussian process. What we observe is some linear combination of these latent processes. So that's why it's called the linear model of co-regionalization. It's co-regionalization because all the Gaussian processes are defined over the common parameter space. So they have to be defined over the same set of parameters, so kind of no blind spots. It is linear because the relationship between what we observe and these non-observable latent processes is linear. The way that the LMC model defines this relationship is through the special matrix, which is defined like this one. So the logic here is that these diagonal elements give the relationship between the latent process and the task that corresponds to that. And these terms, the matrix W multiplied by itself transposed, this is basically the off-diagonal terms. That means how the latent variable 1 corresponds to the task, to the different tasks. So this is just a parameterization, so it can be chosen to be much more complicated, but kind of that's already difficult enough. So in this case, we have the latent variables which we cannot observe, much like in the variational autoencoders. These latent variables are Gaussian processes, so this gives us handle on how to learn them. And as the Gaussian processes, they are characterized by the usual kernel length, kernel scale, and so on and so forth. We don't know what they are. That's a normal problem in the latent variable models. But what we do know is that these latent processes can be combined in a linear fashion to give rise to the observations that we can make. So the linear connection is important because that's something that we can learn. So when we have the multitask Gaussian process, what we try to do is we try to learn the usual parameters of the Gaussian process, the kernels and so on, but we also try to learn the elements of this matrix B. So we learn the linear relationship between the observables and the non-observable Gaussian process. So in some sense, think about it this way. The classical Gaussian process is the surrogate model on something that we can measure directly. We assume that there is no hidden truth that we don't have access to. Our observation is the direct measure of the ground truth by noise. The multi-fidelity Gaussian process says that we have two fidelities, high fidelity and low fidelity. We can observe one or the other, and they are somehow correlated through just one parameter. So it's useful in many cases, but limited. The multitask Gaussian process says that there are latent variables which can be complicated. It can be one-dimensional, it can be two-dimensional, it can be more high dimension. We don't have access to them. All we know about them that they exist and they have the property of the Gaussian process. What we observe is some linear combinations of these latent variables. These are our observations, and for convenience, these observations are parameterized as this type of linear matrix. So that's the idea. So as the result, our model becomes considerably more flexible when it comes to the real world applications. And the example that I'm going to show you, it's very difficult to kind of illustrate this flexibility. It sort of requires a little bit of a jump of imagination. But I'll show you the examples of how it works. Limitation is, of course, for human perception. We can observe only things in the essentially one dimension. So we don't get that many opportunities to, we don't have that many degrees of freedom to visualize such complex concepts. But let's see how it works with a simple case. So we provide the usual inputs and some error handling. And then let's look at the toy dataset. So this is the problem where we assume that we have a cheap theoretical simulation that we can perform over the entire parameter space. And we have the costly experiment that we can measure only in the some parts of the parameter space. So in this, notice that this is a core generalized model. So we assume that the parameter space for theory and experiment is the same. It's just that theory can access all of it and experiment can access part of it. So the theory and experiment don't match by 100%. So what we want to do is to use this multitask Gaussian process to learn the correlation between the theoretical simulation and experimental observation. So that means that we want to learn this matrix B and use it to predict in the unmeasured part of the parameter space. So this is how the problem is formulated. So what we do is to define our theory and experiment function. We ascribe the fidelities for these models. We say that the experiment can be, that the theory can be measured everywhere. Experiment can be measured only from 0 to 25 and from 75 to 100, but not in between. We create the ground truth, and this is how it looks like. So what you see here is the theoretical model. This is our fidelity 1. This is the experimental true function. So this is what we want to discover. This is our fidelity 2. And the points is our experimental data. So we have theory measurements everywhere that we don't even show the individual observation. We have the experimental observations only here. Notice that the function has certain structure. So there is this oscillations, and therefore our idea is that the algorithm should learn that there is a correlation between how the experiment changes and how the theory changes, and it will try to reconstruct the experiment using the knowledge of the theory and partial knowledge on the correlations. So let's see how the regular Gaussian process will look like. So if we run the regular Gaussian process, this is just exact GP. We train the model, we make a prediction with the model, we plot the result. So the result is kind of underwhelming. So what happened? Our kernel parameter is okay, so it's relatively short-range correlations. But basically what we see is that if we have the data, the Gaussian process, of course, have reconstructed the function reasonably well. In the place where we don't have the data, the simple Gaussian process did the only thing it could do. It says that, you know what, I determined the kernel length. I cannot predict the behavior of the function further than the kernel length. And I say that the function goes like this, but what I can say is that this is the uncertainty. So I don't know much. I just tell you that the uncertainty is large. So there is no relationship between the ground truth and the simple GP because the length scale of these waves is simply larger than the kernel length, so the GP cannot discover it. And there is no way for the normal GP to predict that these variations will exist somewhere here. So now let's see what happens if we use the multi-task Gaussian process model. So in this case, we need to be much more careful about how we define the model. So the first thing that we can do is to define the number of the input dimensions, kernel, And that actually has to be 1. So sorry, I ran it twice. So that practically should be the one latent function. So once we are going to, and we also need to define the rank of this matrix. So the rank of the matrix tells us how many linear parameter we think connect our task 1 and task 2. So once we run the process, we get the values for this parameters. So of course, they are in the form of the prior distribution. We have the parameters for, so let's just run it and see what happens. I'm run before. So, but anyway, so sorry, this was for 2. But okay. So while let's see how long it will take. This should be actually fairly fast. So we have the inputs, we defined our functions. So now we are going to get our Gaussian process. So this is, we already seen this one. So now let's see how long the multitask Gaussian process is going to take if we define one parameter. So that's fairly slow, but we'll get there. So anyway, while it's calculating, this is what we are going to see. So in this case, as you can see, the match between the theoretical model and the ground truth, the ground truth for the experimental data and the model is actually fairly close, because the algorithm learned from the theoretical dependence, and it was able to identify the structure in the predicted function learning from the theory model. And as you can see, that the relationship between the ground truth and the prediction is actually very close, and in fact that the uncertain interval covers it all. So let's see how far. Okay, so let's see how far along. Okay, so now let's see what happens if I calculated it only for one latent. So in this case, the number of the parameters in the matrix is much smaller because we have only one latent process. But if I'm going to look at the prediction, see what happens. So in this case, you can see that with the one latent variable, the model is more rigid. So there is a larger difference between the ground truth and the prediction, but we still were able to capture the behavior reasonably well. So what else can we do? We can use exactly the same approach to run the Bayesian optimization. And so this is an example of how it is going to work. So this is, we define our ground truth function. We define the initial measurements. We define the certain help function that allows us to run both the classical GP and the multitask GP. So this is how the progression of the normal Gaussian process-based optimization look like. So we start with observations, and we get our posterior mean and uncertainty. We calculate acquisition function. We keep going through the cycle if we do it enough times. So it can be very illustrative to go through the steps and just kind of check your knowledge and understanding of the Gaussian processes. But in the end, we are going to reconstruct our function in the usual way. So we've already done it many, many times. This is the end result. You can see that this is an optimization problem. So we found the minimum. We generally sampled the whole parameter space as well. Now, how we're going to do that if we have the multitask Gaussian process? Well, in this case, we actually need to make our data structure a little bit more complicated because we have the theory versus experiment. So we need to define which one we are going to measure. So we define our priors for multitask noise and for this coupling function. So it's an initial parameter. We define our acquisition process, and this is how the process is going to work in this case. So if we look at the progression of the multi-objective optimization, then we calculate we have two latent variables. So these are the parameters that we want to learn. We learn this matrix that relates our latent variables to our observables. And this is how the progression is going to look like. So we run the BO loop. We learn all these parameters throughout the process. And after we are done, this is what we are going to get. So this curve is the true function. These are the points where we have done the measurements. So these are the simulations that have been used to inform our measurements. So you can see that simulations actually helped us to find the minimum of the true function. And that's actually great because that made our measurements much, much faster. We spend most of the time actually exploring the true minimum of the function. And then if you want to see how the posterior samples look like and sort of see what's under the hood of the Bayesian process, here it is. So let's stop at this point, and I would be happy to take questions.